Welcome to Real Learning Center. This is the second session of our kinematics and plotting the graphs. Now we shall see here that we are going to today talk about XT and VT graphs. So we have learned in the first session about how to plot a graph for a given equation. Okay, so any equation, a line equation, and we also learned what is the meaning of y-intercept and what is the meaning of slope, all these things in the first session. Okay, so now we are going to use that in physics to basically plot graphs for XT and VT graphs. Okay, that is this session, second session. So let's see. Let's start with something called as an XT graph of 1D motion. Okay, now let's understand this a little bit before going ahead. The 1D motion actually simply means one-dimensional motion. Means it is going in just one single line. Okay, it is not actually going like this, or it is not going in a some kind of a circular path or nothing like that. Okay, it is going a straight line. That is a 1D motion. Okay. Now, what we are going to plot is an XT graph. So x here, t, as you know, t signifies time. Okay, so that is we can measure it in seconds or minutes or hours. For standard purposes, we always take it as seconds. And x actually is, we will use two words for x. I keep using them alternatively. One, I call it as position. So whenever I say x is a position, I mean it's a position. Its position with respect to some origin. Oh, okay. Somewhere there is the origin there. From there, where is its position? That is called x as a position. Sometimes I call it as x as a displacement, which is also right, because displacement is nothing but from the original position where it has moved, the direction and the magnitude. In both cases, x actually is suitably used. We call it either as a position or as a displacement, provided we take the original position as the origin. If you take original position somewhere else, then position and the displacement are not same. Okay. In this case, basically we are talking about a situation where O is the starting point, okay, where it is the origin. So we can use both words interchangeably here. Okay. So now XT graph of 1D motion, I start with an ant. Okay, here is an ant resting well in on point O. Okay. Now the ant actually moves through this line. So let us say how the ant moves. Okay. Ant starts moving from point O, and it will actually reach point A in about 4 seconds, and it takes 3 seconds rest, and then moves to point B in about 10 seconds. Now see it again, it goes from point O to A, okay, in 4 seconds, 20 centimeters it covers in 4 seconds, then it takes a 3 seconds rest. Okay, after taking 3 seconds rest, it again moves for next 30 centimeters at within 10 seconds. So now I want to plot an XT graph of such a 1D motion. So that means at every point of a time, like after 1 second, after 2 seconds, after 3 seconds, where was the ant? I want to see that. So that is basically called an XT graph. Where was the ant after every small interval of time? So that is called an XT graph. So to plot a graph, we need actually a graph sheet. Okay, here is the graph sheet. So on a graph sheet, basically we are going to take an x-axis and a y-axis. We have seen that we used to take x-axis in the horizontal, y-axis in the vertical, and when in our last session. Now here we are giving different names. Okay, so the horizontal axis we call as time axis, it's a t-axis, and we measure it in seconds. And vertical axis is actually my x-axis. X is no vertical. Okay, it is measured in centimeters. Now, whatever graph we are going to plot is not actually the map of how the ant moved. Okay, map is different from a graph. Here we are showing at every point in time how far the ant has moved. That is our how far is measured in the x-axis. At what time is measured in the horizontal axis. Okay, I will call it as vertical axis, horizontal axis. Now, I have already drawn the graph. Okay, you can see. Okay, the graph is that from O to P, you can see O to P, then there is a line which goes like this. What is the meaning of that? Okay, the meaning of that is at time is equal to t, t is equal to 0, okay, and it is at O. So we have put a point at O. Okay. Now, after 4 seconds, that is, okay, if you see on the on my t axis, every square is 2 seconds. After 2 seconds, after 4 seconds, like that. After 4 seconds, it is at what point? It is about 20 centimeters. So now my vertical axis is actually 10 centimeters, 20 centimeters, 30 centimeters, like that I have marked. That means 10 centimeters is one level, 20 centimeters is second level. So that means you can see very clearly that it is at P. After 4 seconds, it is at P. Okay, so mark a point at P. Now, after another 3 seconds, which is another 3 seconds means here in this case 1.5 units of time. So it is still at the same point, that is 20 centimeters from the origin, okay, from the beginning. So that also I have put there, just basically Q, point Q. Okay. And after another 10 seconds, that means you can count 10 from there, and from there you see where it has reached. It has reached, okay, 30 centimeters plus 20 centimeters, 50 centimeters away. So it is at 50. That is the point R. Now, if you see that P, O, P, Q and R, those are at the end points. But in between also it is moving, and every point in time if you keep taking, it is going at a constant velocity during those times. So the line you can join like this. So that would basically be our XT graph. Okay. Now I would like to basically show you the corresponding time where the ant is and where the graph is. So please watch the ant and the graph, okay, and the line, and see the corresponding time where it is. Okay, let's start. The ant starts. Okay, the ant keeps moving, and you can see the yellow line going up. And between P and Q it is stationary, but the line is moving because time is moving. Okay, and after that Q onwards it is moving slowly, and the line is also moving up. So that is how the XT graph is drawn. Okay, for the ant moving from O to A and then to P. Okay, now after having drawn that, okay, that's easy enough to draw. Okay, after having drawn that, let us do some little bit of analysis on what we did. Okay, so we have already learned all these lines. Here you can see that OP is also a line, PQ is a line, QB is another line, QR is another line. So these lines, we have understood that lines have equations. So how are they going to be useful here? Let us see. Okay, let's start with basically OP as a line. Okay, take OP as a line. So this line, okay, I'm going to write an equation for this line. Okay, that equation is x is equal to mt plus c. Why am I writing this? So you know, in the last session we talked about lines. So y is equal to mx plus c, like that I wrote. Y is equal to mx plus c. But now there is no y. In the place of vertical y, we have vertical x. So in the place of y, I put x. So instead of y is equal to, I say x is equal to. Now instead of mx, I will say mt, because horizontal is time. So mt, and c remains as it is. Okay. So this is my equation of this line. And what are the values of m and c? C is a y-intercept. We know where it is cutting y-axis. So this line is cutting y-axis at 0. So we call C to be basically y-intercept is 0. Okay, that's 0. Now, what about the m, which is slope? So what about the slope? Slope is, you can see very clearly that it is the rectangle, the triangle that we take, right angle triangle that we make there on that line, and we will measure them. The values are actually 10 and 2. So each box basically vertically is 10 and horizontally is 2. So 10 divided by 2 is our slope. M is equal to 10 divided by, which is 5. Okay, M is equal to 5. That's the slope. So we can write the equation now as x is equal to 5t plus c. We replace m and c with 5 and 0. Okay. 5t plus 0. That is the equation of the first part of the line, OP. Okay. Now, what is the use of writing such an equation? Okay, so let us see what is the use of writing the equation. We will also write the equation for other two lines. Okay. So for PQ, so that means basically for our journey from O to A. Okay, that is the line OP. OP signifies our journey from O to A. Okay, which is x is equal to 5t plus 0. So our taking rest, the ant is taking rest. While it is taking rest, okay, the line on our xt graph is PQ. Is only time has moved. It has not moved in the upward direction. It is horizontal. Okay, it's a horizontal line, which slope is actually 0 for a horizontal line. Okay. And its y-intercept, where it cuts y-axis, is if you take the PQ and just put a dotted line and see here on the y-axis, it cuts at 20. Okay, so y-intercept is 20. So similarly, okay, so the third part is x is equal to 3t minus 1. Okay, this how we got 3t minus 1 here. I want you to basically figure that out. I am not going to tell you. This is for the line, for the journey from A to B. For the ant journey from A to B is signified, is basically given by the line QR. The line QR is having a slope of 3 and a y-intercept of 1 is what I am saying. So please figure that out. Okay. So these are the three equations we have got. Okay, and these three equations of these lines are going to be useful. Okay, now going forward, I will explain how they are useful. So now we got an xt graph. We will see to draw a VT graph. Okay, and see what is the meaning of a VT graph. VT graph is similar to xt graph in terms of we are plotting it on the graph, but what we plot is different. Horizontal axis is time only. On the vertical axis, we are going to plot velocity of it. That means, suppose assume that the ant which is moving here has a speedometer tied to its head. Assume that it has a speedometer, and if you keep taking the reading for the speedometer, okay, so what is the value? So that speed or the velocity, what we call it, including the direction, is what we are going to plot, not where it is, but we are plotting how fast it is moving. That is a VT graph. Where it is a xt graph. At every point in time, where it is. At every point in time, how fast it is moving, that is a VT graph. That is what we are going to plot. And you can very clearly see that from O to A, when it is moving, it is moving at a constant velocity. And what is the velocity? We already know. We know how to calculate. Okay, it is taken 20 centimeters in 4 seconds. 20 centimeters in 4 seconds means its velocity is 5 centimeters per second. Okay, so it is moving at a velocity of 5 centimeters per second. That is known. Okay, and is it changing in the path O to A? It is never changing. The speedometer is always showing 5 centimeters per second. Okay, so that is why we are going to plot that blue line. You can see is a mn. Okay, is a 5 centimeters per second. Mn is a 5 centimeters per second line. It is plotted at 5. As the time is progressing, it is still showing 5 only. So it is horizontal line, no change. At the point of A, it takes rest. It comes to a standstill, a grand halt. The moment it stands still, its speedometer comes to 0. Okay. That means that its velocity is 0 at that point. So hence, we are going to draw a 0 velocity. You can see that PQ here is 0. Okay. So for about 3 seconds, it simply shows 0 velocity. After that, it again starts moving. Now when it starts moving, it is going at what speed? So speed is always nothing but distance by time. Now. So 30 centimeters in 10 seconds, which is basically 30 by 10 is 3. So 3 centimeters per second is its velocity. And with that velocity, it will start moving from R. So you can see RS signifies its movement from A to B. When it is moving from A to B, RS is the line. So that RS keeps shows you it is always showing 3 at every point. It is not changing. Its speedometer stands still at 3 centimeters per second. So that is what it shows. So when you reach S, now this is basically what we can see. Now, let us actually see this happening with the ant moving. Okay, so ant moves, and you can see that yellow line coming over there on MN, and it is taking rest, and you can see the PQ is moving, yellow line, and then it starts moving again. This time RS is moving. This is basically a VT graph. Now, let's look at basically three equations that we have figured out in my previous XT graph. Okay, three equations. One of them was journey OA, XT graph equation was x is equal to 5t plus 0. Now you can see that the 5 was the slope of the line, okay, for the journey from O to A. Okay, so from journey from O to A, in the XT graph, it had a slope of 5. Okay. Whatever it had a slope of 5, here that 5 is actually the velocity. Velocity is nothing but the slope of the XT graph. Remember that. Velocity is always the slope of the XT graph. So slope of the XT graph was 5, and hence the velocity is 5. So you can find out the slope, okay, and of any XT graph line and know what is its velocity at that point in time. Okay, so this m here is 5. So now you see here, second one is v is equal to here, so we can very clearly v as 5 centimeters per second, that we know. The second part of the journey is x is equal to 0t plus 20, where it was taking rest. So 0 is nothing but the slope of that xt graph, and hence in the yt graph we are showing that as 0 also. Don't get confused. Basically xt graph shows where it is, and vt graph shows how fast it moves. So I am trying to show you the link between xt graph and the vt graph. Whatever the slope in the xt graph turns out to be the actual value in the vt graph. So you can clearly see here, for the second one is 0 meter per second. The third one, you see, the third part going from A to B, when the ant is moving from A to B. Okay, it is A is equal to 3t minus 1. Okay, that was basically the equation. In that equation, you see the 3 is the slope, and when 3 is the slope, 3 is our velocity here, and it happens to be that 3, that velocity you can very clearly see. So the RS shows the height of 3. So that is 3, and that 3 meters per second is its 3 centimeters per second is its velocity. So now we have shown basically the relationship between these two. Okay. Now we will write actually here go to the next step, where if velocity is changed, so we have always seen that velocity was constant in that one. It started with some velocity, going at the same velocity. Its speedometer is not wavering at all. Check, starts at one point and always at that point. Okay, now we are going to see it is getting accelerated. When you press on the acceleration of a vehicle, speedometer keeps going up. That means its velocity is continuously changing with respect to time. That is the scenario. We will see now what happens. Okay, so I have shown here again a graph, and in this case you can see that the x-axis, the horizontal axis is actually time, and vertical axis is velocity. I am plotting a VT graph to start with. I am not plotting an XT graph. Okay. So how am I plotting the VT graph? Now what is happening here? What is happening here is that there is a car. Okay, and that car, once I say go, it starts moving. Okay, at a constant velocity, and that constant velocity it will move up to the point O. At point O, okay, it will start accelerating. That means at every fraction of a second its velocity is changing. It will start accelerating up to A. Okay, at the point A, it has reached a higher velocity, okay, because it is already accelerated. And after that, it goes at the higher constant velocity, the same velocity. It will not accelerate. So, from up to O and after A, both are constant velocity scenarios, okay, which I am not interested in much. I am interested in from O to A. So I will plot mainly that part. Okay, and in the graph, you can very clearly see the PQ is the line which shows from O to A. So what does it show? It shows that as the time progresses, it shows very clearly that the velocity is actually increasing. Yeah. So Now we have to make sure, we have to now understand how it progresses. Let us see. Okay. So now we'll look at the, I'll start the car and see how it goes. Okay. So it's going at constant velocity, you can see, and it reaches point O and starts accelerating. Now you see it accelerated and reached the A, and after that it went at a constant speed. Velocity after it. So the yellow line, I want you to basically watch it again. Let's watch it again. Okay. So the car is moving at constant speed now, and it goes up to O with constant velocity, and at O it starts accelerating, and from A onwards it goes with a constant velocity again. So the line basically, PQ signifies the change of velocity, continuously changing velocity. Now let's see how do we draw some equations out of it, because the physics is all about basically writing the picture, understanding the graph, and getting the actual how the motion is happening, and drawing the equations for that. This is what we do. Okay, so we'll just look at basically what happens here. Now OA journey is actually given by the line PQ. Okay, OA journey is given by line PQ. Now what happens to this line? This line will draw a equation for this line. Okay. This line is V is equal to mt plus C. So we are actually drawing an equation of writing an equation of a line in a VT graph. Remember, this is a VT graph. So V is equal to mt plus C we have written, because V is the vertical axis and T is the horizontal axis. Like Y is equal to mx plus C, it is V is equal to mt plus C. Okay. So what are the values of C and M? We will see. Okay. C actually is a y-intercept, where it is cutting the vertical axis, vertical intercept. Okay. So it is 1, cutting at 1. And what about M? Okay. Let's take a triangle there again and move the triangle here and see what it is. Vertically it is 1 and horizontally it is 0.5. So it is 1 by 0.5, which is 2. So that is M. Now we got an equation which is basically V is equal to 2t plus 1. Okay. So let's see what is this t2 and what is this 1. So this 1 is the initial velocity. Initial velocity means when the car is at O, before the accelerator is pressed. So that is the initial velocity. So that is 1, okay, at O. And what is 2? 2 is the slope of this, so which we are going to give a name called A, because that slope is acceleration. Okay. So if you draw a line of velocity time on the velocity time graph and write an equation for the line, its slope is always acceleration. Like we have figured out in an xt graph, the slope of an xt graph is always xt line is always velocity. And if you happen to draw a line for a VT graph, its slope is always acceleration. So generically we can write it as V is equal to AT plus U. Okay. V is equal to AT plus U means at any point in time between P and Q, anywhere, if you want to find out the velocity, okay, you can find out how long it has moved, and you can use V is equal to AT plus U equation and find out. Or you can show it on the graph where it is. That is also easy. Let's say after 1 second what it is, you go to 1 second and show on the graph what it is, find out the velocity. Or you can use t is equal to 1 in this equation. 2 into 1 is 3, 3 plus 1 is 4, 2 into 1 is 2, sorry, plus 1 is 3, so V is equal to 3. That is basically 3 meters per second will be the velocity after 1 second. So you can calculate that. Now, so what we will do is this particular equation we call it as one of the most important equations of the kinematics. So this is the first equation of our kinematics, which we use many times whenever we are given an acceleration and time and initial velocity. To find the final velocity, we use this equation. equation. This equation is nothing but the equation of a line of a VT graph, nothing more to it than that. Okay. But remember all the time that the A is a slope which is constant. You cannot have a you cannot have A varying, okay, because for us slope is constant in a line. Otherwise, it is not a straight line; it will be a curved line. Okay. This is not a curved line. So V is equal. This is applicable only when A is constant. Okay. Now, this is our changing velocity VT graph. Now let us see. Okay. What will happen in the xt graph for the same changing velocity. Okay. So let's look at the xt graph. How do we look at the xt graph? So it is the same graph of the VT graph I am showing here. Okay, this is VT graph what I am showing. xt graph I am going to show here down. Okay, on the here mainly because I want to compare it with the VT graph. See, okay, as I am showing here, xt graph. So in here, the vertical axis is x and the horizontal axis is time. Time I am aligning. Okay, exactly like every half a second is basically one square, and vertically I am taking it as 2 meters every square. Okay, that is what I am taking as the vertical. Now, what happens here is you look at basically the PQ region where we are interested. Okay. Now, we will say the displacement, basically x is the displacement that we want to plot. We know displacement is basically velocity into time and all that. Okay. So, now velocity into time basically for a straight line motion, okay, velocity into time, we are not going like this. So, velocity into time if you take, here which velocity will you take? That is the question, because velocity during PQ, okay, that is while travelling from O to A is represented by the line PQ. During that time, velocity is different at different points in time. So, which velocity we are going to take to calculate the displacement? That is the question. Since it is varying like linearly like this, let us take an average value of the velocity. Okay. So, if we want to do x is equal to v into t, velocity into t, we will take an average value, okay, of velocity. What is the average value of velocity? So, we can't take the final velocity. Okay. We have to take velocity at p and velocity at q, and rather velocity at when it is at point O and point A. Okay. So, that is u and v. So, half plus initial velocity plus final velocity divided by 2 is what we are going to take, half of u plus v. So, instead of v I am going to write half of v is wrong, v is only final velocity, we cannot take. Okay, so, we have to take half of u plus v into t. Okay. So, that is actually, if you see, we are taking a middle velocity at m. Okay. Half of u plus v is actually m, at m. So, we are taking a velocity at the point at m, middle velocity, okay, and multiplying that with time. So, that probably will give us a good answer to how much is the displacement. Okay. So, if we take v, which is basically the velocity at any point in time, actually if you see is u plus a, that we have just now shown, at plus u is what we have shown in the earlier slide. So, we can actually substitute in the place of v u plus a. So, here is a little bit of algebra that you can work it out, u plus a, which is 2u plus 8. Okay. Then do distributive law and basically multiply. What you will finally get is x is equal to ut plus half at square. Okay. So, this is the formula for x at any point in time given t and u and a. Yeah, x is equal to ut plus half at square. Now, what we can do is we can actually start substituting the value for t and calculate x and plot on this. Now, how are we going to do that? So, let us say first we have to know what is the value of u and a, that we have already seen from our previous calculations, that is u is actually 1 meter per second and acceleration is 2 meter per second square. Now, what we are going to do is we will give values to t. T is equal to 0, if you give x is equal to 0, that will come at the first point. Second point is we will give t is equal to 1. So if you put 1 square into 2 into half, is basically nothing but 1, plus 1 into 1 is 1. So basically 2. So when you give t is equal to 1, you will get x is equal to 2. So that we will plot as 1 point. Okay, and then we will plot another point for t is equal to 2. So if you plot t is equal to 2, you get another point, which is basically at 6. So now these 2 points, if you see, you can put more points in the middle. Give 0.5, 1.5, all that you can put points. And then if you join them, okay, how do they look like? They don't look like a straight line. Okay, so what do they look like? Let's see how they look like by actually running the car. Okay, so the car actually moves exactly like how it used to move, and it starts accelerating here. And the first one shows the velocity graph, second one shows the displacement graph. You can see now that the part from basically what we call in the displacement graph, if you see P to Q, is actually a parabola, a curve like this. Because there is a square term in the T that we have discussed. Whenever there is a square term, we used to get parabola. Okay, so we got a parabola now. And then from Q onwards, it is going at constant velocity. Again, it's a straight line after that. Okay, so this is basically how the xt graph looks like when you have. So let's try to understand this. It is like this: the velocity is changing. Okay, and hence if you look at basically the xt, okay, that means the position, the distance traveled by the car. Initially, it will travel lesser distance, okay, for a given time. The first 1 second it travels lesser distance. The next 1 second it already is picked up the speed. It will travel more distance. Hence, you see the curve going up like this. Yeah, more and more distance it gets covered for a given small time, when it goes forward. So this is basically what we call a second equation of our kinematics. And instead of x, we can write s also. Displacement is given as s. S is equal to ut plus half at square. This is another equation which we can use to solve many problems. So we have covered basically first equation, v is equal to u plus at and s is equal to ut plus half at square, and shown you graphically what it means. Now let us look at some of the important common situations where xt and vt graphs can be plotted. So when an object is at rest, and when object moving at constant velocity and object moving at constant acceleration. Okay, what is the meaning of constant acceleration? Constantly changing in velocity. Changing means it may be increasing, it may be decreasing. If it is increasing, it is called positive acceleration. If it is decreasing, it is called negative acceleration, okay, or a deceleration. So the first one, object is at rest. So this is basically our first plot, where xt graph, if you see, the first one being an xt graph, you can see that it is at rest, means it is at the same place at every point in time. So it's horizontal line. At rest at some distance, let us say at some distance from the origin, it is at rest. Okay. So the second one you can see is velocity. Velocity is 0 all the time. It is at rest. So from the beginning till the end, it is 0. That is object at rest. What about object moving at constant velocity? So object moving at constant velocity means its position is continuously changing. So that is our xt graph, but its velocity is constant. That is our vt graph. Okay. And an object moving with constant acceleration, where positive acceleration means we just now saw how the parabola is coming into picture. And this is our xt graph, and vt graph is a straight line. Okay. So the slope of this xt graph, I said, is always v. Okay. And initially it is slowly picking up. Its slope is smaller. So when its slope is smaller, we can see the value of v also is smaller, which means in that line somewhere down. As the time increases, value of v increases, which means value of its slope increases. It keeps getting more steeper and steeper. Okay. So this is the point that I keep on repeating, and you should actually think about it all the time. That's when physics becomes easier, understanding these slopes. Okay. Now, what about the negative acceleration? Means initially it had some velocity, you can see by the VT graph, and slowly velocity is coming down in a straight line. So initially it travels more distance, gradually it travels lesser and lesser distance. So that is this kind of a bent curve with bent in the later when it's going forward. Okay, this is basically a negative acceleration curve. Now, let us go. These are some of the common situations. Let us now go and see whether we can do some homework. Okay, let's simple things like, for example, draw the VT graphs and XT graphs for these situations. What are the situations? Situation is freely falling body. A body is freely falling. So can we draw a just drop something, it is falling. Can we draw XT and VT graph for that? And then we see an object vertically thrown up like this, and it is still going up. Can we do a XT and VT graph for that? So try that. And thirdly, we can say a box sliding down the inclined plane. The inclined plane is there, a box is sliding down. Can we draw a XT and VT graph? And let's say you take a ball and drop it here, it keeps bouncing many times. So when it is bouncing, can you draw a VT graph and XT graph for that? Try these things. So you will get better at how to do this. So we have now covered plotting the graphs of any given equation, and then we also talked about XT and VT graphs and the relationships between them. Then next part we are going to do how to analyze these XT and VT graphs a little more deeper and understand how acceleration affects this. So come back and watch the third video on kinematics and graphs. Thank you.